Okay, hello.
Hello.
Can everyone hear me?
Okay,
can you see the presentation?
Yes, we can see it.
Okay, great. Yeah, I mean, so first, thank you for being here and for being invited to have a talk on that. I have to say my background is also more engineering-like than these mathematics of the virtual element method. So I simply want to show why I am, as an engineer, use the virtual element method and for what. I work with polycrystalline materials, and what I want to show here today was initiated by Michele Marino. He's working currently at the Department of Civil Engineering and Computer Science at the University of Rome, Tor Vergata. So I have my apologize if I not pronounced that correctly. Yes, and so the contents are basically the motivation why using virtual element method for.
We cannot see the whole slides.
You cannot see the whole slides. Okay, it's not great.
Control A.
Yeah, I did it. Yes.
Maybe you have to open the screen a little bit more.
Okay.
It's
just part of it.
Okay.
Okay.
This is better.
Is it better yet?
Yes.
Okay. Yeah. Please say if you cannot see everything. It's really important. So yes. So maybe I adapted a bit. So can you see this now? The full slide?
Yes, now it's full slide.
Now it's working.
Okay, very great. So thank you for mentioning, and sorry that I didn't recognize that. So the content is basically a motivation why using virtual elements, at least for polycrystalline materials, which are mostly grain materials at the microscale. Then I introduced the constitutive framework. It's just a few slides to show you, okay, what I employed at the microscale. And I guess this computational approach, since we heard in at least every presentation in the last 2 days here, I can skip a bit and want to focus on representative numerical examples. And I was happy yesterday that I could add a little piece of my current work. I added yesterday because yesterday the computations were done. So I can show something which is really recent here, and it's about periodic boundary conditions on 3D non-cubic domains. So let me start. Why REM for crystalline environments? Basically, it is because crystalline environments are so-called grain-like microstructures. And I have a picture here on the right side, which shows you a microstructure of steel aluminum rods. Maybe you remember, I guess, Franco Brezzi showed it in one of his very first slides yesterday. There was even a better picture of a grain-like microstructure, and these grains can be approximated in computational mechanics for engineering problems, at least, with Voronoi cells. And as we know, Voronoi cells have different number of nodes. We can use the virtual elements for treating one grain, so one Voronoi cell and one grain, as one element, which would give us advantage regarding computational costs, and we see later also regarding accuracy. So the constitutive framework here is electro-magneto-mechanic. It means we have 3 different primary variables, which is U, the displacement, phi, the electric potential, and this other phi is the magnetic potential. We are in linear strain. So we have our linear strain measure, then we have the electric field measure and the magnetic field measure, respectively. And we introduce an elastic energy function, so an elastic potential, which differs for each grain. Why it differs? Because we attach for each grain a different pseudo-random generated orientation, at least. And so every grain, depending on the crystal lattice of the grain, has one or more preferred directions, and then this gives us a kind of anisotropy on the microstructure. We employ a quadratic potential, and we introduce basically these rotations to the micromechanical modulus of each grain, and thus all these values in these micromechanical modulus, respectively speaking, on the main diagonal are the stiffness matrix, the dielectric modulus, and the magnetic modulus, and on the off diagonal we have the piezoelectric modulus, the piezomagnetic modulus, and the electromagnetic modulus. They will be rotated by these R, and Thus, each energy for each grain might differ, which is then anisotropy. And the computational homogenization, since I talk about computational homogenization here, the approach is that we say we have a representative volume element, and our homogenization scheme is based on the fulfillment of the Hills condition, which incorporates volume integrals. And from here on, I refer to either the volume average of a quantity with the bar, or a macroscopic introduced quantity, which has also a bar. So volume average here is for sigma, for D, and for B. And macroscopic introduced quantities is then the epsilon, and the electric field E, and the H bar. So from this, we obtain our macroscopic homogenized material matrix for the full RVE, which is this G bar, and incorporates for sure all of these other modules. We employ Dirichlet boundary conditions such that we have to do up to 12 simulations to obtain the full matrix. The computational approach for the virtual element method is, as we heard many times here, split on the based on the split of the primary field. At the element level, then we introduce these n pi, which collects the constant 1 and the node coordinates in the initial configuration, and these A is the matrix of virtual parameters, which we have to find or have to compute at least. From here, you know, this is a low order ansatz, so linear ansatz, and this means all of these gradients here are already constant at element level. This gives us the advantage that if I have to do a volume average of a quantity which is dependent on these gradients, like the stress or electric displacements, this D, it is basically not an integral anymore, because it is just the volume of the element times this quantity, and this summed up over all elements. For the numerical examples, I want to first introduce my representative volume element. So for these studies, you will see a few slides later, I have this cuboid domain, made of 100 Voronoi cells. In an engineering context, this would mean 100 grains. So you can simply imagine that as sliced out of a microstructure, this cuboid, then observing 100 grains. And on the left side, you see the discretization via the virtual element method. So one Voronoi cell is one virtual element, so equals to 1 grain. In the middle, you just see the submesh needed for the stabilization part, as we also heard at Professor Wriggers' talk, or as from Fadi's talk or Blaž's talk. And on the right side, you see the most finite element mesh of these RVE. So this is a highly refined finite element mesh and has over 350,000 elements, tetrahedral elements at least. And what we want to do now is to compare the volume average of this macroscopic homogenized material matrix, this G bar, for different approaches. So the first approach is the Wem computed on the Voronoi cells. This is then Wem Voronoi for us, and we compare this with the computation of these results on the submesh via a finite element approach, also linear element approach, or we can also go higher order element approach, where you then have not only 4 nodes per tetrahedron, but 10 nodes and more integration points, respectively speaking. And we compare that also to the solution of this highly refined FE mesh of the RVE. So first, electro-mechanically coupled problem at the microscale means that our G bar shrinks a bit down, and we have to do only 9 independent simulations when we employ Dirichlet boundary conditions. And we did this at least for a few different materials. I guess this point group is not interesting for you all. But what is interesting here, at least, is the lattice structure, because the type of the lattice structure is important for where you observe 0 or non-zero entries in these subpart modules here. So, for example, for trigonal lattice structure, you observe different non-zero entries as for hexagonal lattice structures. And also, what is interesting, this A superscript U, which gives the universal degree of elastic anisotropy, means for 0 you do not have any anisotropy, so it's isotropic, and for higher values it is subsequent more anisotropic. So which is really high value here for 140 or 244. And what do we compare? We compare the computational error, as I wrote it here, with respect to an overkill solution, which is these fines. So we compare the norms of these G bar for each method. So FEM01 is maybe you remember from Professor Wriggers' talk. FEM01 is the linear tetrahedron, so finite elements on linear tetrahedrons. FEM02 is then finite elements on tetrahedrons with 10 nodes and quadratic shape functions. And VEM09 is this VEM-VO. Is the virtual element computation, so the low order ansatz for the 100 elements we have in our RVE. And what you can see here in the figure is then basically the finite element solution, this downgoing curve. This is the finite element solution from the submesh. This is the most upper point going to the finest mesh. So we compute here the mesh refinement with the FEM, taking this last solution as the overkill solution, so as the reference solution. And we compare here then FEM01 or FEM02 cores to VEM-09. Please have in mind that this VEM-09 has the same number of degree of freedoms as the finite elements 01 cores. So, I mean, for quasi-isotropic behavior on the left side, we do not observe quite a big error for finite element cores mesh for linear tetrahedrons. But when going more and more in anisotropic regimes, we will observe quite a high error for coarse meshes for FEM, also for quadratic shape functions, while staying really at low errors with the VEM-09 approach. So for us engineers, this is a really advantage, because when we want to homogenize something, we also have to have in mind that this is computational cost which we have to invest. And if we can stay accurate and shrink down the computational cost, this is great for us. Yeah. The next numerical example is a macroscopic electro-magneto-mechanical hybrid material. Means that we have on macroscopic scale, so the homogenized modulus have the full coupled matrix, and the microscopic modulus G for each grain is either piezoelectric or piezomagnetic, but never electromagnetic. So we observe macroscopically an electromagnetic coupling, but on microscopic length scale, we do not observe that for the individual grains. So we have two different materials. We change the volume fraction of the RVE for one material, and we observe basically the maximum magnitude of electromagnetic coupling. This is this alpha bar, or the magnitude of the norm of alpha bar is basically at its maximum at 10 to the power of -3, which is quite high for electromagnetic coupling. So as, for example, natural materials have, I guess, 10 to the power of -9 or something like that. What we compare then is, again, the computational error and for an optimal beta. So maybe I dropped that. At the computations you saw before, we just kept the beta destabilization parameter constant at 0.1. So it was found by Michele Marino in previous works that we can keep this really low value. And now we want to see, okay, when I change the volume fraction, how do I have to change the beta to obtain the most less computational error, which we saw here with the fixed beta 0.1. We are still in a good regime, but if we choose the optimum beta, we can sometimes decrease the error by just 1 order of magnitude. So from this, we can conclude, that VE approaches for these, at least for these polycrystalline environments where we have heterogeneous and anisotropic framework, we have here advantages because we can fit these grain geometries perfect. And we outperform the FE approaches for the same number of degree of freedom at homogenization procedures, also for quadratic shape functions, yes. And this is the conclusion from these two things. And what I want to show at last is from my current work. So now you have heard about computational homogenization. So what you can do with that is either homogenize the material matrix, and take these parts and define at least your macroscopic law, and have then macroscopic law with material parameters from homogenization. Or what you can also do is have a two-scale scheme. It's something where you apply the load on the macroscopic framework and solve the computation simultaneously in macroscopic framework and microscopic framework. For finite elements only, it would be Fe squared. Okay, so for that, periodic boundary conditions is an advantage. Why? Because we know that periodic boundary conditions have a better convergence rate, and so the convergence rate would then influence our full convergence rate of the two-scale problem. The problem here is that if we have RVEs, we would have unstructured mesh. Means that we could not apply node-to-node periodic boundary conditions, but we would have applied node-to-surface periodic boundary conditions, right? You can imagine, like, if you have a cube and you have on one side a node, and on the other side you will find at the same position of the cube you will find the surface. So you have to use the interpolated displacement on that. What we can do with them, and this is two things what we can do here, is we can treat non-cuboid domains. As you see here, the domain itself is periodic, which is the assumption of an RVE basically. So put these RVE much times together and you will observe the macroscopic structure. Since this RVE is periodic in its structure itself, this means that every corner point, which in virtual element formulation is a node for us, every node has a pairing node, which means that we have node-to-node formulation even for this unstructured geometry, and I would say unstructured mesh. So which is a great advantage because we can apply periodic boundary conditions, and we will have no additional nonlinearity because we have node-to-node formulation in these periodic boundary conditions. How to construct that on these RVEs? You have to find on the boundary at least 3 nodes, so 2 node pairs incorporating the same node. These are these black points here, where these blue arrows are drawn. So you have 2 node pairs which incorporating the same node, and then to this you add 5 nodes, arbitrary, I would say placed, because the only thing for periodic boundary conditions what matters is the distance of 2 nodes, because you can strain 2 other nodes on the boundary, because you constrain only the difference between 2 other nodes on the boundary with the difference of direct constrained nodes. So direct constrained nodes would be these 8 nodes directly constrained by a macroscopic deformation measure, which is then transferred from the macro to the micro scale. And since only the distance of these nodes is important because you constrain parallel node pairs, you just can place the nodes arbitrarily where you want. And since every node on this surface of the domain has a pair, you can apply node to node. So how you can evaluate if this is right when you compute that? Since everything here is based on the Hill condition, simply use the Hill condition. Means for isotropic material, even if it's geometric nonlinear, it has to be that the volume average of the microscopic deformation gradient has to be equal to the applied macroscopic deformation gradient. So in this case, so means you have a constant strain, constant Green-Lagrange strain, yeah? And also a constant first Piola Kirchhoff stress. This is this PM. And what you see here is the E11 component of the Green-Lagrange strain for an applied macroscopic deformation gradient, which has F11 equals to 1.1, and the rest is unchanged. And it's exactly what you would attain for the Hill condition. So this works, and the great advantage is that contrary to FEM, I go to this slide again, contrary to FEM, here you would have to mesh really fine, and you would have to use either linear displacement or uniform traction boundary conditions. But with them, without any pre-processing, I mean, except adding these 5 nodes there, which is not a big part, you can easily introduce node-to-node periodic boundary conditions, which is great for your convergence in a 2-scale scheme. And also, you have no additional pre-processing, which also, which also fastens your routine. So with that, I want to conclude my talk. Here are my references, and this is the acknowledgement. So thank you for your attention.